Welcome back. Today we are going to see some propositions which are important actually. So let P and W be real vector spaces and T from V to W be a linear map, then these following three statements are true. First one, kernel of T is a subspace of V. Second one, image of T is a subspace of W. And the last one is T is 1 1 if and only if kernel of T is equal to singleton 0. Now you might remember while explaining the definition of kernel of T, I have already told you that kernel of T is a subset of domain of linear transformation and image of T is a subset of W. Okay, so before proving kernel of T is a subspace of V, let us recall the definition of subspace. So if we are able to prove these two conditions, then we will say that W is a subspace of vector space V. Now in this case we have to show that kernel of T is a subspace of V. So in order to do it, first of all we have to show kernel of T is non-empty, right? Next we will show that kernel of T is a subset of V. Next we will show that these two conditions are true. So we will take two elements of kernel of T. We will show that their sum also lies in kernel of T, and we will show this second condition as well. Okay, so there are no issues for the subset. Kernel of T clearly is a subset of V. Now the question is, why kernel of T is non-empty? So first of all we will recall the definition of kernel of T, then we will show that it is non-empty subset of V, and then we will go for these two conditions. So chalo, let us start. So first one, okay, we know what is our kernel of T. Our kernel of T is a collection of those elements of V such that T of V is equal to what? 0 of W actually, but I will simply write it to be 0. Okay, so why kernel of T is non-empty? So I will write it here as T is a linear transformation. Okay, therefore what is T of 0V? T of 0V is equal to 0 of W. If you want I will write it 0 of W over here also. Fine. Now since T of 0V is equal to 0W, so therefore meaning of this is image of 0 is nothing but 0, and you already know which elements are present in kernel of T, those elements of V that are mapped to 0. So over here which element of V is mapped to 0? This one, right? So therefore 0 of V belongs to what? Kernel of T. Since it is mapped to 0, therefore kernel of T is non-empty, right? Clearly kernel of T is a subset of what? V. Now we will go for the two conditions of subspace. So for the first condition we need two elements of subspace, but over here we have to show kernel of T is a subspace, right? So I will take two elements of kernel of T because we have to show kernel of T is a subspace. So I will say let U comma V belonging to kernel of T. Okay, I hope you are getting this. This belongs to be any elements Now since u and v are present in kernel of T, so therefore what will be T of u and T of v? In other words, what will be image of u and v? The image of u and v will be 0. So therefore the image of u will be 0 and image of v will be also 0. Right? We have to show that this u plus v belongs to kernel of T. What is the meaning of this? That is T of, now see, when this element will go and sit in kernel of T if image of this element is equal to 0. The meaning is T of u plus v is equal to what? 0. So I will start with LHS and I will prove that it is equal to RHS. So I will call it as some star. This will be needed later on. So I will say consider LHS, that is nothing but what? T of u plus v. But T is a linear transformation, so therefore this is equal to T of u plus T of v. Since T is a linear transformation, so therefore this is equal to 0 of w plus 0 of w. This is from star, right? From star we are saying that this T of u is 0 and T of v is 0. So that fact we have used, but you already know this is nothing but 0 itself. So that is our RHS. So therefore this u plus v belongs to kernel of T. Now let us go for the second condition of subspace. So I will say let alpha belonging to R and u belonging to kernel of T be any elements. Now since this u is present in kernel of T, or you can say since u belongs to kernel of T, so therefore what will be image of u under T? It will be 0, right? I will call it as some double star. Now what we have to show here is, we have to show this alpha u belongs to kernel of T. So what is the meaning of this? We have to show that the image of alpha u is equal to what? 0 of w, right? So logic is same as we have done previously. So I will consider LHS and I will prove that it is equal to RHS. So I will say consider LHS, that is nothing but what? T of alpha u, which is equal to what? Alpha times T of u. What is the reason? Since T is a linear transformation. But what is our T of u? But our T of u is 0 of w. This is from double star, right? And this is nothing but 0. And that is our RHS. So therefore, you can say that alpha u belongs to what? Kernel of T. And thus, what we have proved? Kernel of T is a subspace of V, right? Now we will show that this image of T is a subspace of W. That is nothing but what? Image of T is non-empty, then image of T is a subset of W. Further, image of T satisfies the conditions of subspaces. Now, while discussing the definition of image of T, I have already told you that image of T is a subset of W. So what I will say here? Clearly, image of T is a subset of W, right? Now we will show that it is non-empty. Just remember, while discussing the definition of linear transformation, we have seen one proposition, that is 0 is always mapped to what? 0. And while explaining the definition of image of T, what is our image of T? Image of T is a collection of images of elements of V. Means whenever you are having an image of V, simply take image of that and that will give you what? The element of image of T, right? So As we already know, since I'll say since V is a vector space, since V is a vector space, therefore it is going to have a zero element, so therefore it belongs to V. Now since we are having a element of V, so simply take image of that and you will get a element of image of T. So I'll say therefore this T of 0V belongs to what? Image of T. But what is T of 0V? But T of 0V is 0W, since T is a linear transformation. Therefore 0 of W belongs to what? Image of T, like this, right? Brackets everywhere, and therefore image of T is non-empty. Is that okay? Now we will go towards what? The conditions of subspaces. Now note one thing. How do elements of image of T look like? They are of the form T of V. Now in order to prove the first condition of subspace, we need two elements of the set that we have to show that it is a subspace. So in this case we have to show image of T is a subspace, so we will need two elements of image of T, right? But elements of image of T look like this. So I'll take two elements of image of T as T of V1 and T of V2 for some V1 V2 belonging to what? V, right? So let us start. So the first condition of subspace, I will call it as some A if you want. So I will say let T of V1 comma T of V2 belonging to image of T be any elements, right? So what we have to show? We have to show or to prove this T of V1 plus T of V2 belongs to what? Image of T. Now just note one thing, when this element, that is T of V1 plus T of V2, will belong to image of T, it will belong to image of T if we are able to show that T of V1 plus T of V2 is of this form. This form means what actually? T of some element of V, right? So we have to show that this element is of the form what? T of some element of V. So what I will do is I'll say consider T of V1 plus T of V2, which is equal to T of V1 plus V2, since T is a linear transformation, right? Now see, we have shown that this T of V1 plus V2 is of the form T of some element. Now the question is it an element of V? If it is an element of V, then we can say that element belongs to image of T. Actually this V1 plus V2 is an element of V. Why? Because V is a vector space. So therefore this V1 plus V2 will be a element of V, and therefore it will belong to what? Image of T, since V1 plus V2 belongs to V as it is a vector space. Okay, so this is regarding first condition. Now we will go for the second condition of a subspace, right? So just a minute, I need some space over here. So yeah, I think that will be enough. Okay. Now just remember the second condition of subspace. For the second condition of subspace, we need one element of R and one element of what? The set that we want to show subspace. So in this case, that is image of T, be any elements. What we have to show? To show this alpha multiplied by T of V1 belongs to what? Image of T. Now, same reason. In order to show this element is in image of T, right? We have to show that this element can be written as T of some element of V. Why? Due to this. T of some element of V. Okay. So, it is easier to do that. So, simply I will say consider. I will say consider this alpha times T of V1, but this is equal to T times alpha V1. What is the reason? Since T is a linear transformation. Okay. Now I can directly say that it belongs to image of T. What is the reason again? Since this alpha V1 belongs to what? V, as it is a vector space. Okay. So yeah, vector space, that is what we wanted to prove. So therefore I will say image of T is a subspace of W. Okay. Now let us go towards the third part of this theorem or proposition. Okay, so we have to prove that T is 1 if and only if kernel of T is equal to singleton 0. So chalo, let us start. Remember, it is if and only if. So first of all I will assume that T is 1, then I will prove that kernel of T is singleton 0. Later on I will assume that kernel of T is equal to singleton 0, and then we will prove that T is 1. Fine. So let us start. So before going ahead, let us recall few things, okay, that will be required in this result. So when do we say that T is 1, right? So whenever T is said to be 1, if T of V1 is equal to T of V2, implies V1 is equal to V2, right? For V1, V2 belonging to what? V, isn't it? So whenever you are having T of V1 is equal to T of V2, immediately you can say that V1 is equal to V2. Okay. Now I will say that I will write here, this is part 1, that is the if part. Suppose T is 1, and what I have to prove? I have to prove that this kernel of T is equal to what? Singleton 0. This 0 is of vector space V, so either I can write it like this, or even if I don't write it, it means that it is of V only. Okay, so let us start. So in order to prove kernel of T is equal to singleton 0, so we have to show that kernel of T is a subset of singleton 0, and this singleton 0 is a subset of kernel of T. Okay, so first of all I will show that this singleton 0 is a subset of kernel of T. So as we know kernel of T is a subspace of V, right? Now remember, subspace means vector space only, okay, according to the basic definition of a subspace. So therefore it is going to contain the 0 element, right? Now since 0 belongs to kernel of T, therefore you can say this singleton 0 is a subset of kernel of T. I will call it as some 1. Okay, I hope you are getting this point. See, why the singleton 0 is a subset of kernel of T? Because every element of this set is present in kernel of T. How? Because this set contains only one element, which is that 0, and just now in the step before this we have shown that 0 belongs to kernel of T. So therefore this is happening. Now I will take an element of kernel of T and I will show that it is present where in this set, that is singleton 0. So I will say let some u belongs to kernel of T, right? Now just recall the definition of kernel of T. What is our kernel of T? Kernel of T is equal to like this, right? Kernel of T is set of all v belonging to V such that T of V is equal to 0, isn't it? Now since this u belongs to kernel of T, therefore what can I say? Whenever some element is present in kernel of T, then its image is equal to what? 0. So therefore image of u, that is T of u, will be equal to 0. So in order to be more precise, I will write it as 0v, just understanding purpose. This has 0v, this has 0 to the suffix v, and over here you might remember the definition, this is 0 to the suffix w, so therefore this will be 0 to the suffix w, right? But recall one more thing, we have T of 0v is equal to 0w, as T is a linear transformation. So this value I can use, right? This value, which one? This value I can use here, okay? So therefore I can say that this is equal to T of 0v. That is nothing but what we are having, T of u is equal to T of 0 to the suffix v. Remember this one is suffix, okay? Yeah, like this. But T is 1 1, right? Now since T is 1 1, what can you say immediately by using this? So therefore this u should be equal to 0 to the suffix p, right? But okay, where does this 0v belong? This belongs to this singleton 0 to the suffix v, right? But this 0v is nothing but u, so therefore this u belongs to what? This singleton 0 to the suffix v, right? So what we have proved actually? So we have started with an element from kernel of T, that is u, and we have proved that that element is present where? In this singleton 0. Therefore we can say that therefore this singleton, therefore this kernel of T is a subset of singleton 0 to the suffix v. We'll call it as some 2. So therefore from 1 and 2, what can you say? We can say that this kernel of T is equal to a singleton 0 to the suffix v. That is what we wanted to prove. Okay. Now let us go for the part 2 of this result. So I will assume that suppose our kernel of T is equal to what? Singleton 0, and what we have to prove? We have to prove that T is 1 1. So as explained before, in order to prove T is 1 1, what we have to assume? We have to assume that this T of v1 is equal to T of v2, and we will prove that this v1 is equal to v2. Okay, so I will say let T of v1 is equal to what? T of v2 for this v1 v2 belonging to vector space v, but this implies this can be written as T of v1 minus T of v2 is equal to what? 0 of w, this is w, so this implies, but T is a linear transformation, so we can write it as T of v1 minus v2 is equal to 0 of w. This is because since T is a linear transformation. This implies, now note one thing, so we are having image of some element equal to what? 0. So whenever image of some element is equal to 0, so what can you say about this element v1 minus v2? See here, observe this carefully. Whenever t of v is equal to 0, where is this v present? This v is present in kernel of t, right? So over here what we are having, t of v1 minus v2 is equal to 0. So where will be this v1 minus v2? This v1 minus v2 will be present where? In kernel of t. So this implies v1 minus v2 belongs to what? Kernel of t. But what we have assumed, our kernel of t contains only one element, that is 0. So therefore this v1 minus v2 should be 0 only, and this implies v1 is equal to what? v2. That is what we wanted to prove. Therefore t is 1 1. Okay, so that ends our proposition. Now note one thing, this result is very important. So whenever we have to prove t is 1 1, t in the sense what? A linear transformation. Whenever we have to prove that certain linear transformation is 1 1, we can show that kernel of t is equal to singleton 0. म्हणजे फक्त kernel of t is equal to singleton 0 जरी दाखवलं तरी that is enough to prove t is 1 1. हे काही केसेस मध्ये proving t is 1 1 becomes difficult. So in that cases we will prove kernel of t is singleton 0, and in some cases in order to show kernel of t is equal to singleton 0, even if we show t is 1 1, that will also work. But remember, this is true if t is a linear transformation. Okay, so that's all.